Hello everyone, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the products you see around you every day. If you think you know something about these items, you might be surprised. There's a whole new world of things waiting to be discovered here on How It's Made. Caffeine is not for nervous types, let me tell you. To get rid of it, green coffee beans are blown through water steam. The swollen beans are then washed in water to release solvents or active carbons. Finally, they're roasted. A decaffeinated cup of coffee contains 25 times less caffeine than a regular one. On today's show, holograms, package printing, skin culture, and canned corn. Printing variations of an image in layers, then having light reflected from those surfaces at different angles is basically how you produce a hologram. Sound mysterious? Not for much longer. A hologram is a three-dimensional photograph produced by the interference of two laser beams. A laser emits light, this light ray. The color of the light varies according to the wavelength. A shutter, when activated, either blocks the light ray or lets it pass through. Here the beam is split in two at a 90-degree angle. The interference of the two beams is clearly visible on this screen. It has very defined fringes. The beams need great stability because the pattern of interference projected on the screen is extremely sensitive to minute vibrations. A light tap on the table can easily spoil it completely. The team will create a hologram from this sculpture made of modeling clay. The sculpture is positioned on a support with a magnetic base which adheres to the metallic table. Then they place a glass in front of the object. Here's the exact point where the light beam passes. The table has to be perfectly stable, so it's made of a 2.2-ton block of steel, which rests on 18 air tubes. The table and laser are thus well insulated from all vibrations. The beam splitter separates the beam in two, directing one behind the object and the other in front of it. One part of the beam heads toward the front of the sculpture. The beam first passes through an objective lens, which diffuses the light. Then it's reflected by a parabolic mirror, which prevents it from losing too much of its intensity. As in photography, film is required. This holographic film is attached to a glass plate with adhesive tape. Then another glass plate is added so that the film will not move. A vibration of 1/10 of the laser's wavelength is tolerable. Now the laser is turned on. The intensity of its light ray reaches about 250 milliwatts. The normal exposure time of the model to the beam is about 1 second. But some holograms, made with a pulsed laser, are exposed to the light for 12 nanoseconds, an infinitely short period of time. Here we see the reference beam coming from the parabolic mirror. And here we see it from another angle. As in photography, the film has to be developed. These trays contain different chemical solutions and the developer. First, the film is soaked in the developer for 2 minutes. This solution blackens the silver salts, which have reacted to the light. Then the film is soaked in a solution called bleach to completely eliminate the silver salts, which blackened it. Now the film is rinsed. This step is used to eliminate the acids in the emulsion and to not contaminate the next solution. the film gently becomes transparent. It's then rinsed in clear water, and it's soaked for 1 minute in a wetting agent which eliminates all water spots. The film is then dried and it reveals its secrets. And here's the hologram created from the sculpture. A hologram really creates a three-dimensional illusion. Some holograms can be animated. They are generated from a series of still holograms. Depending on the complexity of the project, a hologram can be produced in between 1 and 5 hours.
Printing on packages isn't just the listing of ingredients or instructions. It's also the complex art of product identification, as well as creating an appealing, attractive look for the consumer.
All consumer products are packaged, and the making of these packages starts with the burning of an aluminum plate like this one. This animation illustrates the burning process, the transfer of an image onto an aluminum plate. The plate is placed onto a cylinder, and using a laser, the burning begins. The image appears in 6 minutes. This plate will make the printing impressions on packages. The laser which did the burning has to be perfectly calibrated using this test plate. The plate is now ready to make impressions via the offset method. Printing involves ink, and it requires selecting the right one. If the desired color does not exist, it has to be made up from a mix of various other colors. An ink trial is done with a spatula. And using this small manual press, color ink tests are done. The ink is spread onto paper and the color compared with the one called for by the customer. If the two match, the presses can be started up. This is a 6-color offset process printing press with a 72 by 108 centimeter capacity. The press is fed by a suction and friction process, devouring 8,000 sheets an hour. Now the printing plate is placed onto the press cylinder. This plate will contact inking rollers of the ink reservoir. To prevent it from drying, ink viscosity is maintained with this oscillator. The press starts up and reaches a production rate of 8,000 impressions in 60 minutes. The press comprises individual color printing units. The paper sheet passes from one unit to another, receiving a new color at each step. Here they register the colors, that is, the quality of the superimposition of the different colors. The final step is the folding and gluing of the boxes. This grooved plate makes folding point marks on the carton. And this machine does the cutting, the embossing, and stripping of the sheets at a rate of 6,000 an hour. The cutting die cuts the carton sheets and, together with the grooved plate, makes the folding joints. This sheet is slid behind the cutting die to equalize the cutting of the sheets. This enormous pile of 3,000 sheets is ready to be cut. The embossing press feeder handles between 6,000 and 8,000 sheets an hour. Rollers guide the sheets in the direction of the press. And here, the sheets are embossed by the machine. The precision of the embossing is then verified. Next comes the cutting of the sheets. This goes on at 8,000 an hour. The cutting unit strips and removes the unnecessary pieces, and the carton scraps are sucked up for eventual recycling. The scraps can also be cut away manually by using a hammer. And the carton end pieces are sent off for recycling. All that remains is the assembly of the packages. This high-speed gluing unit can make up 30 to 40,000 per hour. Gluing begins with the folding of the sheets, following the folding marks. The sides of the form box are then glued together. An average of between 5 to 8 steps are needed to fabricate a packaging box. Every day, this plant produces between 1 and 2 million boxes, requiring almost 4,000 tons of cardboard annually.
What would happen if you were severely burned on your hand, your face, your body? A piece of cultured human skin grown in sterile conditions would help healing faster and also lessen the scarring of the burn.
The culturing of skin allows us to save many lives. To grow skin, epidermis cells have to be isolated and made to multiply. It all begins with the removal of a small skin sample. The 10 million cells in this piece are enough to make a culture. The skin soaks in a medium containing penicillin and gentamicin, antibiotics which protect it from bacterial infection. Now a piece of skin is cut and delicately sectioned on a petri dish with a scalpel. The fat is gently detached from the dermis since it will not be needed in the culturing. The skin is cut into thin strips because thermolysin, the enzyme which separates the dermis from the epidermis, acts more efficiently on the small surfaces. Then, an enzyme destroys the links uniting the dermis and epidermis cells. This procedure is carried out in this incubator over 3 hours at a temperature of 37 degrees centigrade. Once incubation is over, the petri dish is removed from the incubator. Only the epidermis cells, also called keratinocytes, are retained. The epidermis is detached from the dermis with great precision. Now the strips are placed in a trypsination unit. Trypsin, an enzyme, will destroy the links uniting the epidermis cells in order to isolate them. This operation signals the cells to multiply now that they're in a favorable medium. In order to increase the effectiveness of trypsin, the trypsination unit is placed on an agitator. The cells do not have to remain in extended contact with the trypsin. They're inhibited with a medium containing serum. Then the liquid containing the cells in suspension is drawn off. Now the liquid is centrifuged to obtain two fractions. The base fraction containing the desired cells is at the bottom of the tube, while the upper floating fraction containing the trypsin has to be removed. This upper fraction is drawn off with a vacuum system. In order to eliminate all traces of trypsin, the culture medium is added to the base fraction and the whole is put back into suspension. Now the cells from the small skin sample have to be counted before being centrifuged a second time. The cells are counted by hand using a microscope or with this apparatus. The exact number of cells obtained during the extraction via a biopsy is determined, as well as the number of cells that will have to be seeded for maximum growth. The bottom portion of keratinocytes is divided in these flasks containing a culture medium whose composition resembles that of blood. The cells will multiply over a week in these flasks, placed in an oven at 37 degrees and at 8% oxygen. The medium in which the cells are immersed is changed every 2 days. In less than a week, the cells have almost covered the entire surface of the flask. They can now be trypsinated anew and thus reseed some 50 flasks, which in turn will be placed in the oven for about 1 week. Skin strips coat the inner surface of the flask. They are then detached with a spatula. The flasks are cut in two with a heating unit resembling a soldering iron. To make handling easier, gauze is placed on the skin strips whose thickness is less than 1/10 of a millimeter. The graft is placed on the wound. Clamps in the gauze will be removed after 10 days. A patient can be skin grafted in less than 2 weeks.
I'm a big fan of corn on the cob, but unfortunately, at certain times of the year, it's impossible to find. Thankfully, corn is also great out of the can. The journey from cob to can is quite something to see. Throughout man's history, food preserving has included smoking, freezing, drying, and salting. In the early 19th century, Nicholas Alpert built a factory to preserve foods in hermetically sealed glass jars and to sterilize them by boiling. But glass was breakable, and so in 1810, an Englishman named Durand invented the tin can, first used by the military in the War of Independence, and soldiers, it seems, first developed the handy can opener. The corn that's canned is harvested from mid-August until mid-October. Canning is done very quickly. Less than 4 hours pass between harvesting and canning procedures so as to conserve much of the nutritional value of the product to be sold. The unloading of many trucks of this size will be needed for the 136,000 tons of corn that are canned here annually. The cobs are transported into the plant on this conveyor. They will first have to pass through a kernel remover. Equipped with several counter-rotating cylinders, this unit removes the leaves and the silk which surround the cob. Within only a few seconds, the cob is completely stripped of its covering. Once clean, the cobs fall into this chute en route to the next processing step. Here they're lined up, ready to be handled by the kernel remover. The kernels are removed from the cobs by going through the machine where knives remove the kernels in a fraction of a second. Each of these units remove 1.5 tons of kernels per hour. Twice a day, the machines are stopped to inspect the blades, to clean and sharpen them. The corn kernels fall into the middle, while the cobs themselves are moved to the sides. Both kernels and cobs move along on their separate ways in the process. The kernels enter into this rotating drum, which removes any particles larger than the kernels. Nothing is wasted in the processing. Corn residues, leaves, and cobs will all be used later as animal feed. Now the kernels fall into a mix composed of water and of a fluid that's obtained when cutting the corn kernels. This liquid mix allows for the transporting of the kernels without damaging them. Next, the kernels flow along this belt and are placed on this conveyor toward the following processing step. Bleaching is done in this huge cylinder. A worm screw brings the bleached kernels to the surface. A visual inspection verifies the quality of the kernels. All that remains is to pack them into these leak-proof cans. Thousands of cans of every size are carried to the filling department. Filling the cans is done from this rotating filling machine. This filling machine can handle 300 to 450 cans a minute. The kernels which fall to the side are gathered up later in this cylinder and returned to the filling line. Here a brine composed of water, salt, and sugar is added. Covers are securely attached onto the containers, but the canning is not yet finished because they have to proceed with some very important tests. They perform tests in this laboratory that assure the quality of the product.
First, they check the water tightness of the cans. They also control the filling weight and the quality of the kernels. In the meanwhile, cans continue wending their way through the plant. One step remains: sterilization. Sterilization takes place in this oven at 121 degrees centigrade and lasts between 4 to 6 minutes. This is a crucial step because it guarantees that the product is reliable and that it will remain so for 18 months. Now they taste samples of the product to determine that it conforms to quality standards. Cans are labeled as customers' orders are filled. In this facility, they produce an amazing total of 43 million cans of corn.
I hope you enjoyed our show today. We wanted to take you behind the scenes into the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made.